Welcome back, AP Calc students. We're going to take a look at problem 2, our final problem in this very short lesson, covering topic 8.3 using the accumulator function and contextual examples of the definite integral. And I really like to connect this to our good old rate in and rate out problems. What you're going to see is a very interesting situation here when you think about the problem that we just did in example 1 with the baby elephant, and now our problem number 2, Janet with the shoveling snow, in that these were back-to-back problems on the 2010 AP exam. The snow problem was number 1, and the baby elephant naming question from the zoo was problem 2. And it was very interesting that both problems had some kind of a rate in and rate out connection, and they both appeared on the exam. So you can see it's a very important concept that we definitely want to make sure we go into the exam and have a bit of confidence. So let's read this. There is no snow on Janet's driveway when snow begins to fall at midnight. From midnight to 9 a.m., snow accumulates on the driveway at a rate modeled by f of t equals 7t e to the cosine of t cubic feet per hour. T is measured in hours since midnight. Janet starts removing snow at 6 a.m. The rate g of t in cubic feet per hour at which Janet removes snow from the driveway at time t hours after midnight is modeled by G of t. And wow, look at that G of t. That's a rough looking rate at which Janet's shoveling snow. And you can see that there are several questions that are going to be addressed, from how many cubic feet of snow have accumulated to the rate of change of the volume, to finding a piecewise function that represents the amount of snow, and finally, how many cubic feet of snow are on the driveway at 9? Let's say Janet needs to leave for work at 9. So lots of different things going on here. One of the things that I would like to address before we get started is the understanding of the role of f of t and g of t. F of t is a rate. It may not look like a rate, but it sure is a rate. So you can think of f of t is what's going in, right? Or maybe a better word is on, like on the driveway. But that's like the buildup of this stuff. Janet will start removing snow, and she will do so at a rate defined by g of x, or g of t. So g of t we're going to think of as the out, right? Or off of the driveway, if you could think of that. And so it kind of gives you an idea about how you would allow these two to interact with one another in order to use them both if a question requires that they both be used. So that's kind of getting the stage set here. So let's think about this. It's midnight. Janet's going to bed. She's got to work the next day. Snow comes tumbling down, falls at this rate modeled by this function, and will continue to do so for the duration, right? Now, at 9 a.m., it says it's going to stop snowing. But prior to that, Janet wakes up at 6, looks out her window, and says, I got to start shoveling snow. So notice how she doesn't shovel any snow for the first 6 hours, because why? She's in bed from midnight to 6. But when she comes out in that first hour from 6 to 7, she's shoveling at a rate of 125 cubic feet per hour. And then for the remaining 2 hours, I guess Janet's getting a little tired maybe, and she slows her pace down. There's enough information here to really, like I said, ask some interesting questions. The first of which, how many cubic feet of snow have accumulated by 6 a.m.? Well, this is probably one of the easier parts of the problem. It's a very quick entry point. And on the AP exam, this was worth 2 points that particular year. And what the student would have done in this question, or needed to have done, is understand that if you integrate the rate at which snow is falling, which is the f of t dt, and do so along the proper time intervals, which in this case would be midnight times 0 to 6 a.m. times 6, there is already a point on the exam for you right there with just that and that alone. Okay, well, let's get the other point. Make sure we type this into the calculator correctly. So I'm going to switch over to the TI Inspire, and I am going to use my ability to define this function only because I have a feeling that we might be using it several times. It is part A after all. So I'll define this as 7 times t times e. And boy, you never thought you would have a cosine as an exponent of e, right? But lo and behold, we have that. And then we do our shift plus. Those of you using a TI-84 would probably be doing Math 9 right about now. So we have from 0 to 6, and then we can just enter that function, f of t. And then lo and behold, we have our answer, 142.275. So we'll return to the document and we'll write that up. That is going to earn the second point. A lot of people will ask, should we put the units? I will tell you 100% unequivocally, yes, you should put the units. Sometimes you might be off the hook in terms of needing to provide the units because it's already in the question, but let's not take the chance. We know that this is cubic feet. All right. Now, if you're wondering, how do we know it's cubic feet? Here's another cool way to think about it. F of t is already a rate, which is cubic feet per hour. The d of t is a time, which is hour. So that causes those to cancel. So you're sitting on 2 points, so we haven't really broken a sweat yet. Janet might have, but we're doing fine. So we're going to take a look at part B. Find the rate of change of the volume of snow on the driveway by 8 a.m. Okay, I like this part. The idea rate of change already implies to an extent that this is a derivative, right? The volume of snow is going to invoke both our rate in and rate out ideas because we have snow falling, we have Janet shoveling. The two of them must interact in order to determine the snow that's there. But note, the question doesn't ask, find the actual amount of snow. That might be coming up later. This is the rate of snow, the derivative of snow. And so what we'll do is we'll return to our little rate in and rate out model up here, and we realize that, well, wait a minute. The rate at which the snow is falling at time 8 is f of 8, and the rate at which snow is being shoveled at time 8, and snow is being shoveled at time 8, is g of 8. And if we just subtract those two from one another, that is going to give us the answer that we want. And I think we can do this with a calculator. The g of 8, just so you know, is 108 constant. And we can compute the f of 8 with the calculator. And so we'll do that. And again, oh, it's so nice that we have that function already defined. In case we end up with some exact values, let's go back here. I could put a decimal after the 8, and I probably should because I don't really want that answer. So I could either hit Control Enter to convert, or what I probably would have been better off is just putting a decimal there. And as you can see, boom, the answer 48.417. But don't forget, we still have to subtract. We still want to subtract that answer. So I just hit the minus button. Basically, that just remembers your last entry, and I can enter 108. And that is my result, everyone. 59.583 negative. So we'll write that up here. Approximately negative 59.583. What we're really looking at here is the fact that Janet is shoveling snow faster than what the snow is falling. So she's actually making some headway in clearing this particular driveway. Now, I would say we probably want a label on this just to play it safe. The label here is no different than the label on either F or G independently, which was cubic feet per hour. This particular part on the AP exam that year was only worth 1 point. So you had to really know your stuff there. And of course, a bald answer with just this result would not have earned credit. You still have to write this down in order to get the full points. All right, guys, let's take a look at our Part C. Part C might be the most troublesome part of the problem. Let H of T now come into the picture and represent the total amount of snow in cubic feet that Janet has removed from the driveway at time T hours after midnight. Express H as a piecewise defined function with the domain from 0 to 9. So we want to keep tabs of all the snow that Janet has removed. Well, the exemplary response for this might be to think about how much snow has Janet removed, say, at time 0. Well, the answer, of course, is 0. It hasn't even snowed yet. So it's kind of helpful to understand that that is where the problem is going to start. That's our entry point. But we also have to understand that the problem is going to have some different phases to it. For example, on the time interval from 0 to 6, on that time interval 0 to 6. Now remember, I've already taken care of the fact of what's happening at 0, so it's good. So I'm going beyond 0. That's why I didn't underline that. Don't worry about your notation here. In fact, anything that I've written so far doesn't even have to appear on your paper to earn full credit yet. But if this is our time interval, then the function h of t is just merely going to be how much snow Janet has removed at the beginning of that interval plus the definite integral from the time value beginning that interval up to t. Not 6, but t, because what I want is a model that will give me the amount of snow removed on any time between 0 and 6. The function g, if you recall, is the rate at which Janet's removing snow. And you probably should put a dummy variable here. It's always a nice idea to not have the same upper boundary, although we will look the other way if you put t's here. There's a big argument to be made that it really doesn't matter. I always try to instill, let's use some other variable. And you know what I want to use? Let's have fun with this. Let's use s for snow. We could have used x just as easily. Okay, what's this going to give us? Well, once again, h of 0 is 0. If we integrate g of s, which by the way is 0, right? Okay, well, what is this going to be then with respect to s? Well, that's going to be 0, right? I mean, let's just think about it. Janet's in bed. She's not shoveling any snow, right? So basically what we've got here, if you integrate 0, you get a constant, c. There is no s to plug in t and 0 for, and you still apply the fundamental theorem of calculus and you have c minus c, right? But I think a lot of you may have been able to surmise this without really setting this up, because think about it. If the girl's not shoveling snow, there's no snow piling up. All right, and that's fine. If you recognize that without all of this work, more power to you. But I set this up so that we can do the other two intervals a little bit easier, because things are going to change now. Because at 6 o'clock, Janet's got her boots on, she's outside, she's shoveling away. And so now we're going to have a different model for h of t. So now h of t would be how much snow Janet has shoveled at time 6, which, by the way, is 0 again. And then we're going to add to that the integral that starts at 6 and ends at t of this g of s function. Well, again, this would be 0 plus, and then the specific function, g between 6 and t, is 125 with respect to s. And if we integrate this, we get 125, plug in times t, or how about I do this, times s. After all, I'm integrating with respect to s. But if I evaluate that from t to 6, this turns out to be 125 quantity, and it's probably just as easy to place the t and the 6 in like that and leave the 125 factored out. So that turns out to be the second piece of your piecewise function. Not bad. Okay, let's finish this up, Janet. From 7 to 9, what's going on with you? So she's still shoveling away. We know that the amount of snow that she's shoveled beginning on that interval will start with h of 7. And then to that, we will add the integration starting at 7 and again ending at a t. Okay, well, what is this h of 7? Well, if we replace the t with 7 back up here, this is what's so cool about this notation. To find h of 7, notice that this is where we are defining 7. H of 7 would be 125 times 7 minus 6, which is 125. Or you could just look up here and say, oh, 125 times the 1 hour is 125. Now, to save some space here, I'm going to go ahead and integrate the g of s that lies between 7 and t, which is this 108. That'll be the last time I scroll, I promise. And we have this 108. And then when we evaluate that from t to 7 and subtract, that's what we get. And to be honest, this would have sufficed for your answer, even though it doesn't have that piecewise function vibe with the notation. It would have been okay. Now, if you want to make this look a more piecewise function-ish, you could set it up or rewrite it over here and just kind of simplify the pieces and say the amount of snow shoveled would be 0 when 0 is less than t is less than or equal to 6, or it would be 125 quantity t minus 6 for 6 less than t is less than or equal to 7, or finally 125 plus 108 quantity t minus 7. And I just got very lucky that I could use that again as my boundary. So this would be perfectly acceptable when I'm going to kind of highlight here in orange if you really wanted to make this look piecewise. But a piecewise function doesn't have to have this brace, right? All it has to have is its sort of restriction and its rule all on the same line tied together. That's a tough part. It was worth 3 points, and I know that on the 2010 AP exam, this problem did not have an exceptional average, and a lot of that was because of this part C. All right, last part. How many cubic feet of snow are on the driveway at 9 a.m.? Fortunately, this one is not quite as bad, although it does borrow a little bit from the previous problem to at least an extent. So to get the total amount of snow at that particular time, 9, what we would do first of all is figure out how much snow has fallen. And that would just be the integration of the rate f from 0 to 9. And I think 9 o'clock is when it stopped snowing, if you recall from the stem of the problem. All right, well, from here then, we would subtract the amount of snow that Janet has shoveled. Well, guess what? We figured out in part C that H is the total amount that she's removed, and we'll evaluate that at 9. And so in order to answer this, we'll have to take on this integral in our calculator. And by the way, knowing to integrate this f of t from 0 to 9 would have earned a point, just that alone. And the last final point is going to come from the answer. So we'll go back to the calculator here, and I'll do my shift plus, integrate from 0 to 9 of f of t dt. Just so you know, that's how many cubic feet of snow fell on her driveway. Now what we want to do is subtract that minus h of 9. Now, we don't have h in our calculator, so don't try to do something like that. So what we're going to have to do is just go back up here and say, okay, if we plugged 9 in for t, we're going to use the bottom piece, and we have 125 plus 108 times 2. Can you remember that? I'm going to have to enter that into the calculator. 125, so we're going to subtract the quantity 125, right, plus 108 times 2. Hopefully you guys can see that there, just at the bottom edge of my screen. And if I put a decimal just to get decimal output, not that we're going to need it, but we end up with 26.334 or 335 that way. So this is approximately 26.335. I will go ahead and round it up. And of course, that would be measured in cubic feet, which is pretty clear from the stem of the question itself. And that, folks, is what a 9 out of 9 would have looked like on this problem from 2010. And there weren't very many 9 out of 9s on this one, mostly because of the latter part of the problem. Piecewise functions are certainly tough in and of themselves, but whenever you invoke a piecewise function in a rate in and rate out, things can get a little bit rough. I know the Test Development Committee tends to like piecewise functions, especially as of late, so it's something that we certainly want to keep working at and get better. So if you like what you see, make sure you hit the subscribe button. This takes care of our topic 8.3, and the rest of the way in this particular unit 8 is all about area volume. So be sure to check those videos out. We'll see you next time.